velocity is that minimum velocity which should be given to a body to escape the gravitational field of a planet. The escape velocity for Earth is around 11.2 km per second. Please remember, it is 11.2 km per second, it is not per hour. Generally students, they make a mistake that if they say per hour, it is 11.2 km per second. When we say this is that minimum velocity, so there is one word is minimum velocity, and the second is it is that minimum velocity which should be given to a body so that it escapes the gravitational field or pull of Earth or the planet what we are talking about. If we talk about Earth, let's say Earth is here, capital mass is over here. So if this is Earth and we throw a body in the upward direction, it goes to certain height, comes back. If we give it a greater velocity, it will go to a greater height and will come back. It is quite possible we give it that much velocity so that it doesn't come back now, that is, it escapes the gravitational field of Earth, if we are talking about Earth only. So when we say this escapes the gravitational field of Earth, it means the interaction between this body of, let's say, mass m and this capital M Earth, that reduces to zero. If that reduces to zero, that it means that there is no force of interaction between the two, and the force of interaction between the two is given by Newton's universal law of gravitation, that is Gmm upon r square. This is not equal to 0, this is not equal to 0, this is not equal to 0. So if we say that this force should be equal to 0, that is the interaction between this body, mass m, and this capital M, that should be equal to 0, and the distance between them is r. So it means the only option we have to make it as 0 is, that is, when r is infinity. So when r is infinity, this comes out to be 0. So indirectly we are saying that is escape velocity is that minimum velocity that should be given to this body from the surface of Earth so that it just reaches infinity. For Earth it is 11.2 km per second, and for Moon it is around 2.4 km per second. Now let's derive an expression for the escape velocity from the surface of Earth. Let's say this is Earth, mass is capital M, and the radius is capital R. We know that is radius of Earth is almost equal to 6400 kilometer, and later on we shall also be using the value of, that is, action due to gravity on the surface of Earth, 9.81 meter per second square. These two we shall be using subsequently. Now if this is a body over here, let's say of mass m, and right now the distance between this and this is, suppose x is the distance between these two, and I am holding it in my hand. I am holding this object in my hand at this level only. So at this moment, Earth is pulling this body in the downward direction with the force equal to F is equal to Gmm upon x square, where x is the distance between the centers of these two bodies, center of Earth and this, and we say the distance between these two is from the center of Earth and this body, that is x. Now if I have to hold it over here, then certainly I also need to apply a force equal to this only, that is Gmm upon x square. I need to apply force onto this, then only it will be stationary. Now what we wish to do is, we wish to take it from here, that is from the radius of Earth to, let's say, to height h. Suppose from here to here, from here to here we wish to take out. So now our intention is to find the work we will have to do in raising a body from here to here without any exertion. We can give it any exertion. If we give any exertion, then certainly over here there is going to be some velocity. We are not going to give any kinetic energy to this body. It is almost a quasi-static process. That is, we are applying a force equal to the force all the time which is being applied by the Earth onto this body. It is just infinitely small, higher than this force. So almost it takes infinite time. But right now we are not bothered about how much time it takes. We make use of the concepts of calculus. Over there we say that is at this instant we will have to apply a force of Gm upon x square onto this. Now we see that this force, when we talk about this force, as the value of x between these two bodies they will change, the force will change. So it means if you have to find the work in moving a body from A to B, that is from the surface of Earth to height h, it means this force is varying. This is a variable force. So it means the work which we have to do from here to here is going to be calculated using the methods of calculus, that is integration. So at any distance x we find the force, then we find the small work which we need to do for a small displacement in this direction. So force is in this direction, we are applying a force in the upward direction. We are finding the work of this force, so we are bothered about this force. We are not bothered about what is the force this is applying. This force gm upon x square is being used to find what is the force we have to apply. So we have to apply this force, we are doing the work, so we are finding the work of this force only. So F is in this direction, the displacement, we have also taken the body from here to here by a small distance dx, so both of them, they are in the same direction, that is the angle between the two is going to be equal to 0. So the small work done in moving a body from here by a small displacement dx is, we know, that is work is F dot dx, and if we have to find the total work from here to here, so what we do is we integrate it. So we integrate F dot dx from where to where. Initially the body is over here, that is at a distance x is equal to radius of earth, and then it goes to x is equal to r plus h. So this comes out to be, F is going to be gmm x square dx r to r plus h. So this is going to be gmm is constant, 1 by x square dx. This comes out to be gmm, this is x is to minus 2 dx with the limits, these limits. So this comes out to be, we know integral of x is to by minus 2 dx is going to be, integral of x is to minus 2 dx is going to be raise the power by 1, and the raised power comes in the denominator. So it is going to be x raised to a minus 1 by minus 1 is equal to minus 1 by x. So this comes out to be gmm minus 1 by x r to r plus h. We take minus out of the brackets, so it comes out to be minus gmm 1 upon x r to r plus h. So this comes out to be minus gmm, first we put the upper limit, minus, instead of x we put the lower limit, that is 1 by r. So this comes out to be minus gmm r minus r plus h over r plus h into r. So this comes out to be minus gmm r minus h, that comes out to be minus h upon r plus h into r. This minus and this minus, that goes off. So this comes out to be gmm h over r plus h into r. As we discussed earlier, one important substitution we shall be using number of times in this chapter on gravitation, that is gm is equal to gr square. This is an important substitution, and how it has come is, we know that is on the surface of earth, if this is a body of mass m, radius of earth is r, and this is mass of earth is capital M, the force of interaction between the two, that is gm upon r square, that is called weight of the body. So from m and m get cancelled over here, so gm is going to be equal to gr square, an important substitution we shall be using time and again. So the same substitution we use it over here. So this comes out to be, when we put gm as gr square, so this comes out to be gr square m into h over r plus h into r. So this is the work done when the body is taken from the surface of earth to a height h from the surface of earth without any acceleration. If h is very small as compared to the radius of earth, that is 6400 kilometer, then it means during this height the acceleration due to gravity will not be changing. Let's see what it comes out to be. So when h is very small as compared to r, so it comes out to be gr square m, this is h, so this is r plus h is equal to r only, plus r. R is 6400 kilometer. Even if we add 1 or 2 kilometers or so, that is value of h, this is almost, practically it is almost equal to 6400 kilometer only. So we can neglect what is the value of h, that is h is very small as compared to r. So r into r square, r square, r square. So this is mgh, so that is it comes out to be mgh. That's why For the small distances, we simply say the work done is mgh, so we don't get into all those calculations, but these are the precise calculations which take care of, that is, how the value of accident to gravity g is changing during this course. So when we say this is the work done, this can be used for any heights. This can be used for small heights also. This can be used for greater heights also. This expression can also be used in finding what is the work we need to do in lifting a body from the surface of earth even to a height that is equal to infinity. And if we are to find the work, total work we need to do in lifting a body from the surface of earth to, let's say, to infinity, the only thing we have to do is we have to change the limits in this expression. That is, it goes from gmm upon x square, that is the same thing, force, into dx, that remains same. That is from now, from the limits they are from the surface of earth to infinity. So rest everything will remain same. We'll just take care of this thing. Let's take this expression, and over here we just change the limits. So this comes out to be minus gmm. So it comes out to minus gmm, bracket is 1 by, now this is infinity. So over here it comes out to be 1 by infinity minus, but this limit remains same because we are still lifting the object from the surface of earth only. So this is 1 by r. So limits what we have taken is r to infinity, rest all the things remain same, we just change this limit to infinity. So it comes out to be minus gmm, 1 by infinity minus 1 by r, 1 by infinity is 0. So this comes out to be minus gmm into minus 1 by r. So that comes out to be gmm upon r. So this is the work which we need to do in lifting the body from this height, from the surface of earth to infinity without any acceleration. This is the minimum work which need to do. To find the escape velocity, now we make use of basic principle, that is, work and energy, they are interconvertible. Work can be converted to energy and energy can be converted into work. Work has a units as joule, energy also has units as joule only. So once we understand that is work can be converted into energy and energy can be converted into work, so instead of we do the work from here to here, why not give it the same amount of energy, so that because of kinetic energy it is lifted from here to infinity. So what is the kinetic energy that should be given over here so as to just reach the infinity is the same amount of work which needs to be done onto the body so that it is lifted from here to here. So it means the kinetic energy we should give is half m, we call it as v escape square, v escape square, and this kinetic energy should be equal to what? This should be equal to the same amount of work that needs to be done to lift it from a radius r, from the surface of earth to a point at infinity. So this should be equal to gmm upon r. If we give this velocity, then this body will start from here, gradually its velocity will be reducing, and as it reaches infinity, it will come to a stop. If we give any greater velocity than this velocity, escape velocity, then over here also this will have some velocity and will this move further also with some kinetic energy. But we are not bothered about it. We are bothered, that is, what is that minimum velocity so that it escapes the gravitational pull of this earth. For that, half mv square is equal to gm upon r. M and m, they get cancelled. It means m, what is m? M is the mass of this body. So it means the escape velocity is not dependent upon the mass of the projected body. So it comes out to be ve square is equal to 2 gm upon r. Once again we know that is gm is equal to gr square. This is the important substitution. So ve comes out to be under root of 2 gm upon r. This can be written as 2 gr square upon r. This comes out to be root 2 gr. So for earth, if we put the value as 9.81 meter per second square and radius of earth as 6400 kilometer, when you put it over here, this escape velocity for earth, it comes out to be 11.2 kilometer per second. This escape velocity is not dependent upon the direction of velocity. Whether you throw it this way or you throw it at an angle of 45 degree or you project it, we know that is on the basis of energy conservation. Doesn't matter in which direction you throw in a body, we still require 11.2 kilometer per second as the velocity that should be given to this object so that it escapes the gravitational pull of earth. Now if you remember from the earlier lecture, we had calculated the orbital velocity for earth for the satellites which are closer to the surface of earth, and that had come out to be a root gr, and it was almost 7.9 or 8 kilometer per second. So it was once again per second. So V escape is root 2 times that of orbital velocity for the satellites which are orbiting Earth at around say height of 200 kilometers or so.